Balanced torque, equilibrium, examples 4 and 5. These two examples will be a lot like problems we'll be doing in the lab with meter sticks. Here we have a meter stick that is balanced with a couple of different weights. In this case, the meter stick is balanced at its center of gravity with this red fulcrum. You'll be using pencils. I'll show you in class. Anyway, what you'll want to do once you've got the whole thing in balance is to draw the simplified free body diagram. What we're trying to figure out here is the weight on the left. For example, let me give you some information. The weight on the right, actually it looks like the little guy. It really should be the big guy because the big guy has to be the one closer to the fulcrum. Now, the one on the right, we will be hanging our masses on these. The masses all have weights. But, for example, if you hang a 500-gram mass, which has a weight of about 5 newtons, over there where that little blue guy is on the right, the fulcrum is supporting here in the middle. Then we have, let's say, an unknown weight over here on the left. I'll just label that with mass for now. We're actually going to, not really cheat, but we're going to take a shortcut here. Instead of weights, we will use the masses here because as long as you're consistent, you can calculate these with masses, even though it's not technically correct. It makes the problem much easier. You'll see. This meter stick is balanced. That's what you'll be doing. Your goal here is to figure out what mass number 2 is. Now the scale on this yellow meter stick is a little hard to see, but let me just sort of make up some numbers approximately to scale of what they have there, where these clamps are attached and so forth. Let's say the mass on the left is at the 20 centimeter mark on the meter stick. All of these are in centimeters. This, and there's 3 locations here, these 3 locations where the 3 forces are acting. What you're going to find in the lab is that the center of gravity of the meter stick is not necessarily geometrically at the 50 centimeter mark. And some of the meter sticks, I'll make one up in this case, the center of gravity is at 51 centimeters because some of these have been damaged or they have holes drilled in them and so forth. So let's not assume the center of gravity is at 50. It should be. 51 is not far away. I'll just use that as an illustration because some of the meter sticks are like that. We have to check that in the lab. And the second mass here, the known mass, is at the 72 centimeter mark. So these are givens or things that you will determine in the lab. What you don't know is M2, that mass. So what we'll do is we're going to calculate the torque with reference to that middle location there. Let me call that middle dot where the 51 centimeters is, I'll call that point A. This is the actual fulcrum now, so that makes the clockwise and counterclockwise a little easier for most of us. So with reference to point A, I'm going to calculate my torques. And I don't have a whole lot of forces here, but here's the outline. We want the clockwise torque to equal the counterclockwise torque. All right, if we hold point C or point A, the middle, the fulcrum of the meter stick, steady, which it does in actuality, the 500-gram mass will try to make the meter stick go down on the right and then rotate clockwise. So the 500 grams, once again, we're going to use the mass instead of the weight, technically not correct, but makes the problem simple. That quote-unquote force, that mass, 500 grams, times the distance from where that is to where the fulcrum is, point A, that is 21 centimeters. And once again, we can do it in centimeters or meters, but as long as you're consistent, you can just go with the units you have there. That's the beauty of some of these torque problems. Equals now the counterclockwise torque. The mass at number 2 on the left-hand side there is trying to make the whole thing rotate counterclockwise with respect to point A. That's that mass. As long as you use mass on the other side, we need to use mass on this side, times its distance from the fulcrum, which is 31 centimeters. So if we multiply 500 times 21, and then divide that by 31, we end up with mass number 2 equal to 340 grams, which is good. Now we don't have to convert. that would be about just over 3 or 3.4 newtons if we did this with weights. Then you'd have to then divide by 10 to get back into the mass, 340 grams, 0.340 kilograms. But we're good here. This is what we were trying to get, the mass that's unknown, and now we know it. Here's another example of what we'll be doing in lab. A meter stick on a fulcrum. They're calling it a stand here. Let me simplify the diagram. All these diagrams are going to look the same in a sense. They start off with a horizontal line to represent the lever, the meter stick in this case. And we have a 100-gram mass. Once again, we're going to calculate this problem with masses instead of weights. We have 100 grams right there. And that is, according to my best approximation, at the 8 centimeter mark on the meter stick. Let me just label that 8 centimeters. The fulcrum here is supplying an upward support force. I really don't care what the force is right now because I'm going to be calculating the torque with respect to that point, and that particular force will have no torque with respect to that point. Just like the previous problem, I didn't need to worry about the force at point A. Anyway, that looks like it's about 32 centimeters on the meter stick. 32 centimeters, the location there. But where's the weight on the right-hand side? Well, it's actually the weight of the meter stick that's holding this in balance. Once again, the principle is this. What you want to do with any object to simplify the problems, you need to, or want to, put the entire weight, or mass in this case, of the object at its center of gravity. Doesn't matter if there's a little bit hanging over to the left, a little bit hanging over to the right, but no matter what the shape of the object, a weird shape like a baseball bat or a car or a person, when you do these calculations, you put the entire weight of the object, or in this case mass, at the center of gravity, and then forget the object after that. So what's keeping this in balance is the weight or mass of the meter stick. And once again, let's say it's the same meter stick as the previous problem, even though it's blue now instead of yellow. This meter stick has its center of gravity at 51 centimeters. But that's an unknown mass right now. We want to find, I'm going to call it mass number 2 again, M sub 2, representing the mass of the meter stick, and that's at the 51 centimeter mark. 51 centimeters. All right, so I have 3 forces again. Let me highlight those in blue. And I could pick any one of those 3 spots to calculate my torque. But it makes the most sense usually, if you know the locations, to pick the actual rotational fulcrum point. I will call it again point A right there, where that upward balancing force is acting at the 32 centimeter mark. All right, so calculating torque with respect to point A. You want your, like always, your clockwise torque equal to your counterclockwise torque. With respect to point A, mass number 2, the meter stick's mass itself, which we assume is all concentrated at 51. So forget the meter stick now. It's the entire mass of the meter stick. M2, which is what we're trying to figure out here, and you'll be doing this in the lab. It's that mass. Once again, we're taking a shortcut. We're not converting that to force or weight right now. But times the distance to the rotational reference point, point A, and that is what, 19 centimeters? 51 minus 32 equals the counterclockwise producing weight or mass, that's 100 grams, times the distance from the 100 grams mass to point A, and that is 24 centimeters. Once again, what you'll do now is take 100 times 24 and divide by 19. Mass number 2, rounded off to 2 sig figs, is 130 grams. That would be the mass of the meter stick, and we do not need to do any conversions now. That's the beauty of leaving it all in grams.